All right, let's talk about something that trips up pretty much everyone at some point. You know when you punch a simple calculation into your phone, and it spits out this crazy long number with a ton of decimal places? Well, which of those digits actually mean anything? That's what we're digging into today. We're talking about significant figures, and they're the key to telling the real, honest story behind your numbers. So here's our game plan. First, we'll tackle why more precision isn't always better. Then we'll get into decoding the digits themselves. After that, it's the really tricky part, the rules of zero. Then we'll put it all together with some math, and finally, I'll show you how to craft that perfect final answer. Let's get to it. All right, so first up, the problem with precision. Look, our calculators are amazing tools, right? But they have this little habit of giving us a totally false sense of accuracy. They just throw this long stream of numbers at us, but here's the thing. Not all of those numbers are an honest reflection of what we actually measured. So check this out. A super simple calculation, 6.35 divided by 4.0. Your calculator, it doesn't hesitate. It tells you the answer is 1.5875. But can we trust that? Are all 5 of those digits for real? How do we know which ones are actually meaningful and which ones are just kind of digital fluff, you know? That's exactly the problem that significant figures are here to solve. And that brings us right to our solution, significant figures. Honestly, the best way to think about them is like grammar, but for numbers. They're just a set of rules that help us report our results honestly and show people exactly how much we can really trust our own measurements. Okay, so here's the textbook definition. A significant figure is any digit in a number that we know with some degree of reliability. It's all about communicating certainty. So if you see a number like, say, 13.20, that last zero isn't just there to look pretty. It's telling you, hey, I measured this thing and I'm confident all the way out to the hundreds place. It's a big deal. All right, let's ease into this with the first couple of rules because they're super easy. Rule number 1, any digit that isn't a zero, it's significant. Done. So in 1.234, all 4 of those digits count. Easy, right? Rule 2 is just as simple. If you've got a zero that's sandwiched between 2 other non-zero numbers, it's also significant. Think of a number like 102. Those 2 zeros in the middle, they're totally part of the measurement.
Okay, let's be real. It's the zeros that make everyone's head spin, right? Where a zero is sitting in a number can totally change what it means. But don't sweat it, we're about to make this whole thing crystal clear.
So here we have the 3 main cases for our tricky friend, the zero. First up, leading zeros. You know, the ones at the very beginning of a number, like 0.012. These guys are never significant. They're just placeholders showing us where the decimal point lives. Then you've got trailing zeros, but only the ones that come after a decimal point, like in 0.200. These are always significant. That last zero means someone measured it carefully. And finally, the big one, the ambiguous case. Zeros at the end of a big number with no decimal point, like 50,600. Were those last 2 zeros actually measured, or are they just telling us the number is in the 50,000s? We just don't know.
So how do we fix that whole ambiguous zero problem? Well, scientific notation comes to the rescue. It's the perfect tool. If we write 50,600 as 5.06 times 10 to the fourth, we're screaming, hey, this number has exactly 3 sig figs. If we write 5.060 times 10 to the fourth, that's a clear signal for 4 sig figs, and so on. Scientific notation just gets rid of all the guesswork. Okay, so you've got the hang of spotting sig figs. Awesome. But now for the real test, using them in actual calculations. This is where the rubber really meets the road and where we make sure our final answer is just as honest as the numbers we started with. When you're adding or subtracting, forget about counting sig figs for a second. It's all about decimal places. You look at your numbers and you find the one that's the least precise, the one with the fewest decimal places. Your answer can't be any more precise than that. So with 100 plus 23.643, that 100 is only good to the ones place. So even though the calculator gives you this long decimal, our honest answer has to be rounded to the ones place. That's 124. Now, for multiplying and dividing, we switch gears completely. It's not about decimal places anymore. Now we go back to counting the total number of sig figs. So in this example, 3.0 has 2 sig figs and 12.60 has 4. Your answer is limited by the number with the fewest sig figs. In this case, that's 2. So our calculator might say 37.8, but we have to round it to just 2 sig figs, which gives us 38.
And really, this quote just says it all. The accuracy of a calculated result is limited by the least accurate measurement. Think of it like this. Your calculation is a chain, and a chain is only as strong as its weakest link. Your final answer can never be more precise than your least precise starting number, period. We are in the home stretch. We've done the math. We know how many sig figs our answer needs. There's just one last little thing to do. We've got to round it correctly to give it that final, polished, honest form. Now, most of these rounding rules you already know. If the next digit is bigger than 5, you round up. If it's less than 5, you leave it alone. But what if it's exactly 5? This is where it gets a little weird. The rule is you round to the nearest even digit. So 11.5 rounds up to 12. And 12.5 also rounds to 12. It sounds strange, but it's a really clever trick to prevent skewing your data one way or the other over a ton of calculations. All right, time to put it all together. Let's tackle a gnarly one. We've got division. We've got addition. It's all mixed up. We're going to need every single rule we just went over to get this one right. So you plug all that into your calculator, and this is what it spits out, this long, messy string of digits. And here is maybe the most important pro tip of the whole day. Do not round in the middle of a problem, ever. Keep all those messy digits in your calculator and only round one time at the very, very end. And the correct final answer is 8.6. So wait, how did we get there from that long decimal? Well, because we have mixed operations, we have to think carefully. We have two division problems inside an addition problem. For addition, the rule is about decimal places. So we have to figure out the precision of each term we're adding. The first term is that 5.00 divided by 1.235, the result is good to the hundredths place. The second term is 3000, which is good to the thousandths place. But the third term, 6.35 divided by 4.0, that's our weakest link. Because 4.0 only has two sig figs, the result of that division, 1.5875, is really only reliable to the tenths place. So since the tenths place is our least precise position out of all the terms we're adding, our final answer must be rounded to the tenths place. And that's how we land on 8.6. So I'll leave you with this thought. Sig figs. They aren't just some random rule to memorize for a test. They're about something much bigger. They're about being honest. They're about understanding the limits of what we actually know and communicating that clearly. So now that you know the rules, what story are your numbers really telling?